Cool. So as Oliver just said, I think this last talk it's a bit different from what we have been hearing this week. So I hope it's kind of even if it's not something you're actually working on, I hope it's interesting or opens up a bit of like other opportunities, other things you could do to use. In this case, ultrasound as complement or something together with PMG, with your studies. So as I was saying, we have a few topics for today. Motivation, just so you guys know about it, but just to start. And then I think that's the important bit, because I know this is not an ultrasound audience. I will spend a considerable amount of time explaining the basics of ultrasound and just everyone getting the same point so we know what we're talking about. And then we can go over at one of the first applications I'll talk about. It's using ultrasound for decomposition, which is kind of a different way to do instead of high-density. We take a break, and then we talk about some kind of quickly about some translational prospects, like taking ultrasound for like a more big system that you can only use a lab. If you had to use this in a wearable everyday format, what would you do? How could you do it? And it kind of leads to the second application, is that about interfacing. So controlling human-machine interfaces. Specifically, I'll talk about prosthesis, but I can kind of be more general than this. Then we have the questions and we are done. So motivation. So quick one, interfacing with the brain, extremely challenging. You have to somehow record signals from the brain, understand them, super complicated. But if you decide to interface via the muscles, that everyone here basically, a lot of people here does, it's a bit easier. So that's what we want to do. Normal way to do this, EMG. So as everyone does it, it works. And people have thought about this and done a lot about this. There's just some examples of wearable interfaces using EMG, very famous ones, very new ones, other not so much. But I think this is an interesting topic, right? This is the Mayo armband. I think most people know about it. It released in 2014. And I think when I was making the presentation, I found this article from like, I don't know, a tech article, just as the system released. They're promising to revolutionize the way you interact with computers. But, to be honest, it's been a long time and we're still not there yet, to be honest. Things are still advancing, but it's still not the point. So the reality is that while you interface with the muscles can be less challenging, it's still a very, very tough job to do. It's not simple. That's basically why we're all here. And some of these challenges can be attributed to the signals you record. So if we're talking about specifically SMG, it's an amazing technology, but it has some inherent limitations to the signal. As Silvia mentions, everyone mentioned, you record from the surface of the skin, you're kind of limited to what you can find in the surface. Your spatial localization of what you were recording is not that great. There's a lot of crosstalk. Deep muscles are, depending on how you do it, basically inaccessible. So maybe a way to kind of surpass these limitations and do something different or something that could in some ways be better is using a different technology. And ultrasound, very interestingly, can actually record very nicely the muscles. Like some people have shown it. I think some people even use ultrasound to put the grid zone in the right place. You can record muscles very well. It's very easy to do it. So, okay, could we use ultrasound for interfacing? And that leads you to what is ultrasound? So let's explain basics of ultrasound and go for it. So first, how it works. Very simple. You have a transducer. It's normally a piezoelectric transducer. You apply a voltage to a crystal, a transducer crystal. It vibrates, sends a sound wave that goes to the tissue. And I think maybe we all heard like in high school about Fresnel law and the reflection. So it's basically the same thing. When it passes from one medium to the other, the ultrasound reflects. The wave reflects and you have something back. Not only reflects, it transmits. Not everything is reflected. And also it scatters if the medium is not like homogeneous and not like a very simple textbook case. And that's basically what ultrasound is about. It's about transmitting these waves that we generate. And specifically medical ultrasound, it's interest about mostly the reflections. So we're most interested in transmitting something at a certain angle, normally kind of perpendicular to the interfaces we're looking for, and then receiving the reflection back, the echo, as people call it. That's kind of how you do this. But in practical senses, how normally ultrasound works. So one important thing about ultrasound, the signal itself, the signal you record, it's not biologically generated. It's not like a biosignal. You are recording biological things, so the muscle shapes, the morphology, whatever, but the signal itself, you are generating it. This means that unlike EMG, there is just like the recording phase. You're just put it on, I'm recording. Ultrasound has two phases. Ultrasound has a transmission phase where you transmit something, and then a receiving phase where you receive something back, which is kind of very, in the sense, very different from the EMG perspective, where you're just recording all the time. So how does this transmit, receive, like paradigm work normally? So we start transmitting something. Imagine like the simple case scenario. You have a transducer, a single crystal, whatever, in a water bath. We say water because water is like an easy medium to go for, very similar to the body one. We have at some point, deep distance from it, a metal reflection, like a metal spike. We first transmit something. So something like this. We create like a voltage pulse that when vibrates the transducer creates this kind of a sound wave. It is important to know that this happens very fast. When I mean like a microsecond here, I mean like that's kind of doesn't really happen. It tends to be way, way faster, nanoseconds here. It tends to be very, very fast. So you send this, you kind of send this voltage, create a very short pulse. And because, again, you create this, you can tune a lot about this pulse. You can change the center frequency you send. You can send the bandwidth of the signal. So if it's like a short, a long one, you can send the voltage, meaning you can send higher or lower signals. And everything is kind of tunable depending on what you want out of it. You send a signal, now the signal will transmit. So we'll go and start walking through the medium you are transmitting, eventually hit something, and then, as I mentioned before, you got the reflection back, right? So if you were to, as soon as you stop transmitting, if you immediately switch to receiving, to recording, what would you see? You would see something like this. So you see a period of time where nothing happens, and then suddenly you have this pulse, which is the reflection you send, right? And I think that's the kind of basically the thing that makes ultrasound, the physics behind the ultrasound work, is that the speed of sound in a tissue is constant. So because you know more or less the speed of sound, you know more or less the distance that this echo is. So based on just waiting from transmission, you know when you transmit, waiting a bit of time until you receive something, you know the depth of this. So in a sense, you convert the time to a depth dimension. So you're actually recording time in a sense, but it's like a very, very fast time sample, and it kind of gets converted to the depth. In case here, it's 2D because the signal has to walk distance D and then walk back distance D. So it's 2D is the distance to the reflection you get. And you can kind of fairly simply convert it and have more or less ultrasound, medical ultrasound is interest between like recording for 10 to 200 microseconds, which tends to be from 2 centimeters to 15 centimeters on the scale. That's depending on your application, you do different depths. So it kind of depends on what you want to do. All right. And that's how ultrasound works. To the same point as before, ultrasound, you generate everything. You create your transducer, you create your arrays or whatever, you create your pulse sequence, your frequency, everything. That means there's like an enormous amounts of ways to do ultrasound. There is probably infinite amount of methodologies you can use to record the signals. And there is absolutely not enough time to talk about all of them. And also I would not be able, like no one would be able to tell you about all single methodologies. It's just kind of like in the MRI field, people are experts or like they know about a couple acquisition methodologies. It's kind of impossible, every single one, just because there's so many of them for so many applications. So specifically, I'll mention these three. So we call A mode, N mode, and B mode. They are maybe together with Doppler. They are kind of the basic ones. The first ones people invented, and the ones you tend to see more in medical fields, literature, and people using them. I will not talk about Doppler specifically, but I'll talk about these other three here. So what that is. There's a very nice animation I found that kind of shows the difference between these three methodologies, right? So on the top here, you have to imagine this is a piezoelectric crystal, so your transducer, your channel. A channel is a good analogy. And you have at different distances, 3 different reflectors, 3 different scatters. If you're talking about A mode ultrasound, it's very similar to an EMG channel. You have a line where you have some pulses, which are kind of your scatters in a one-dimensional line. So just literally record the line, kind of a single line going, and the distance from each scatter is your reflection. Very simple, very straightforward. what happens is that if instead of one of these, you have multiple of this, then you can make an image out of this line, right? So imagine you can have like different ones that, one here, one a bit below, a bit below, a bit below, and you can make an image out of this. And that's the one I think everyone knows about. That's the one you see in hospitals, the theta ultrasound. That's basically the one people use it because it's better to look at an image. It makes a lot more sense. So it's kind of a good way to do. The last one is less used right now. It used to be more normal in medicine like 30, 40 years ago. It's called M mode. So in the M mode ultrasound, we are just still having one, normally transducer, and we are doing an A line. But now the reality is that we can make an image out of time. So remember, if you go back, there is this time depth here, right? You convert this short time to depth. But it's important to know that ultrasound has also like the other time factor, right? You can do this multiple times. So you do this now, in 1 millisecond in the future, you do this again and again and again. It's like the frame rate, right? So I think that's something that kind of like makes a lot of people kind of confused a bit, is that basically most of what you are recording on ultrasound is time, but you can convert one of these dimensions, depending on like the range of time you have, to that. Meaning that there is a depth dimension and a time dimension that are like basically decoupled because one is extremely faster than the other. When you're talking about frame rates, we're talking about millisecond scale. When you're talking about depth, we are talking about microsecond scale. All right. So as I mentioned, the mode, you do a line, but then you do a second line, couple, I don't know, 1 second after, half a second after, it doesn't matter. And you make an image out of this. So that's more for investigating how things move over time inside our body. Maybe a simple thing, we are breathing, you put the ultrasound here, you can see the walls of the lung moving back and forward, or depending on how you put against the heart, that was one of the first applications, you can see kind of the pulsation of the heart, kind of the heart rate via this M mode one. And it's way easier to look at it because you have this kind of obvious image of the change in the shape. Another image showing both of them. So we have the A mode, one line, M mode, tracking over time, and the B mode, in this case, is like a diverging one, so you have like this open angle. And this is just to highlight the fact that like, in a simple way to understand this, A mode is like one of the lines of the B mode image. So a B mode image in the simple sense, not necessarily true for every situation, in the simple interpretation, is just a collection of A modes at different kind of angles or different places. So you have like this extra 2D spatial dimension that you don't have with the A mode. And now for B mode. And that's something important to talk about. There is a lot of ways to make these images, but there is an easy way to separate them both in two groups. So there's the thing we call conventional, nowadays conventional ultrasound, which people call scanning or line-by-line scanning. And then there is a bit more recent approach called ultrafast B mode or ultrafast ultrasound. And they differ a bit on how you do this. And it's kind of important to know about this to understand a bit of the next applications and why they work at all. So let's talk about conventional. As I was mentioning before, the normal way to understand it, and that's kind of the normal way because that's how people used to do ultrasound in the very beginning and still do it, is doing line by line scanning, right? You have your array of transducers, you transmit a kind of a line, not necessarily one transducer, you normally do with a couple transducers, so you can do some, it's called synthetic aperture, you can focus it and have like a narrow line, but you transmit basically line by line, right? You have one line, and then you make a second, and you slowly build up your image until you have a full image. And it works fantastically. If you go to a hospital now, basically all machines will do this. That's basically the way you do it. That works simply. There's basically the image quality is very good. This specifically because you can kind of focus them. So you can make every line kind of very narrow and very thin. And you have like a good sequence noise ratio because of that. However, to build this image, now you kind of have a second problem, right? Normally when you transmit it, you transmit and you have to wait until you receive it back, which is fine. It takes a couple, 100 microseconds, but that's all right if you just do this once. If you have a normal probe in a hospital, it would have somewhere from 126 to 256 transducers. You have to do this 256 times to build a single image. And if you do some quick calculations, you know the speed of sound, you know the lines you have to do, so 256, you know more or less the depth you're investigating, so how long you're waiting for each line, you arrive at some frame rate, so 60 frames per second, which most applications is fine, but it tends to be limited, right? That's basically the most you can do. It's not like something you could improve by just better hardware or better system. It's like an inherent physical limitation of ultrasound in that case, because there is just no way, you cannot make sound move faster. Sound moves the way it moves in the tissue. Yeah, it's kind of, you're limited to that. So in this approach of recording, it's basically impossible to go over a couple hundred frames, depending on the depth you do and some tricks you may use. You're kind of limited to that. However, there is a different way of doing ultrasound. So what you can do is now what people call ultrafast ultrasound. Is that instead of sending a pulse with a field, like a line of pulsing, you excitate your transducers all at the same time. So you send something we call a plane wave. So if you send everything together, the wave front is plane because each individual transducer sends like a semicircular wavefront because the sound propagates in all directions. But if you just transmit them all basically at the same time, so exciting all the same time, the wavefront that is hitting the tissue is plane. So that's why it's a plane wave. And in this case, if you apply some smart delays to the channel, you can tilt your plane wave. So you can have a wave that still has a plane wavefront in this case, but it's a bit tilted, right? You make this one a bit shorter and then this one a bit later, like very, very small delays. You can tune the angle you are transmitting this plane wave. And just like the other ones, you transmit a number of them. So like maybe one, like 5-degree kind of, deviation in a sense. You make a plane one, and then you go to the other side and make another one. When you do this, you would normally have some like horrible images. You wouldn't kind of see much because if you think about it like from a kind of physical standpoint, right? At this point here, the reflection could, the reflection that each transducer is receiving could be from any point in the line because the wavefront is kind of, walking towards the tissue like in all the senses. So you don't have that kind of, you technically lose a bit of the spatial resolution. However, you can do something to put them together in a sense. And from these individual plane waves, you can make an actual image with normal resolution that looks amazingly. And now you can see why it is faster, right? In this case, we don't need to transmit 250 something times. We can just take a couple of plane waves. So you can change however you do. You can literally do this with one plane wave. It works. You can use a couple more so you have a slightly better image. Any way, shape, or form, you are up to maybe 20, 30 angles, which is same equation goes, but now you have not number of transmissions, you have number of angles. Then you have a lower number of angles, meaning you can do a considerably higher frame rate, which is the way you kind of unlock like a whole new range of applications for this. Now you can image things in the millisecond scale, not in the kind of just general hertz sense. And one maybe interesting point is that this is not like a new thing. Like, the first person that proposed ultrafast, and they call ectotomography system, it was like 40 years ago. So that's not really new, but it's been present in research and kind of maybe now hospitals a bit more recently, right? And that's because of a very specific thing. So if you look back at this image, right, maybe you remember I just glossed over a bit. You put the images together. So putting the images together is something you call beamforming. You make an image out of this, and that is not very simple to do. So as a kind of this review article here, it's a kind of a book actually, says about it. The reason why kind of in the last 20 or so years, maybe now a bit more, 25 years, we have started to be able to do this kind of ultra-fast ultrasound is because computational advancements. You have easier computational parallel computing power. Now it is easier to record the absurd amount of data you need to record in real time to get this stuff coming. And how easy to save it, accumulate it, and then do your beamforming later. So it's mostly like computational advancements together with like mathematical approaches allow you to do this. I'll not go in details about how beamforming works because beamforming is also extremely complicated. The simplest beamforming approach, which I can kind of explain really quickly, is something we call delay and sum. So it's kind of simple. If you have your image, right, you're building an image. You decide that you want an image with like 100 by 100 pixels. You go for a first pixel, and then you calculate the distance, the distance between each pixel and each of your elements. That means you can apply an artificial delay to the wave you receive it. You can kind of align the wave that each transducer receives to this pixel by introducing a delay to them. And you just kind of sum and average them. And you just go in order and do this for all pixels in your image. And then you can build an image out of this. You can do this by hardware, but it's, I'll say, most commonly done by software nowadays. But it depends on the application. And before I go to the next topic, it's important. Is anything not clear, or is anything that doesn't make sense, or you have any doubts? Because I think if I go to the next topics and you don't understand something about this, then the rest of the talk will be meaningless. So I just want to make sure there's no major questions now, and I can move on.
Why do you need so high frequency?
Under 60 hertz will be probably hard. You don't need 1,000 frames or 2,000 frames, but you probably need somewhere around, I may mention this in this topic, you may need somewhere around 150, 200, 250 frames. We'll talk about that. Again, if you're talking about action potentials, you would technically need way more, like an actual potential intramuscular like 20 milliseconds. So you would need like a couple hundred frames. What you see on ultrasound has a bit more time support, which is around 100 milliseconds, like the mechanical twitch I mentioned. So you should, 100 milliseconds of your full twitch, you hopefully would sample like, at least 250 something to have like a really nice like a result. Yeah. No other questions? Okay. Then moving forward. So, okay, first application we'll talk about motor and decomposition. I think what everyone is interested about. So, what anything has to do? Why would you even be able to decompose motor units with ultrasound? Like, why does this make sense at all? So, probably the first person that did something similar to this was this article for DFIOPS in 2008. So this was with electrical stimulation. So we basically put ultrafast ultrasound probe, so a probe connected to an ultrafast system here on the bicep, and he did some very, 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 very small stimulations to the to get just the tiniest amount of contraction in the muscle. And kind of, because it's electrically stimulated, you can trigger your ultrasound acquisition to your electrical stimulation. So that's what he did. And in the sense, he was able to record something like this, right? So if you see the ultrasound image here, like the cross-sectional image, so you see like a plane crossing the muscle, he was able to see that in some regions, if you were to calculate the velocity, so for every pixel here, if you calculate how much the pixel moved between this frame and the next frame, you could see some movements, like movements up and down, which is kind of what we would expect. If you expect kind of a cross-sectional view of the muscle, you put an image there. Your motor unit, your twitch, will cause the fibers to contract, perpendicular to the muscle. But if you're looking at the other direction, cross-sectionally, you would expect the fibers to bulge, kind of go up and down, and create like an actual movement up and down. So if you calculate the actual movement on the image, an up and down movement, you can kind of see it. And if you look at specific regions, nice ones, you can kind of see this shape here, which is kind of what we would expect from like a mechanical twitch, right? So you have a portion as soon as the spike, that's triggered to the stimulation 0. As soon as stimulation happens, a little bit after, you see these upwards movements, the region moving up with the fibers likely kind of bulging up and pushing everything together. And then they kind of relax back, do a little bit like a backward movement to relax back, and then rest again. So apparently you can see, I wouldn't necessarily say motor units in this case, maybe, but you can see kind of micro transient localized motion inside the muscles. And when you electrically stimulate like very few things, you can see like a very, very repeatable twitch waveform. But it kind of leaves a couple open questions, right? Can we image this during actually voluntary contractions, where you don't have just one thing twitching, but you have a number of units twitching? And the second question is, can this even be used for decomposition? There's decomposition, not just seeing things. You have to somehow be able to separate them enough so you can see the spikes. So what we had, so because of experience with EMG, the Dyer lab had, that's what we aim to do. So important note, this was a lot done by Emma. Emma was a PhD student at the time, a postdoc now. So that's why her image is here. A lot of this was her work with support from other people. So what we did, simultaneous high density EMG and ultrafast recordings. Put two systems together, decompose motor units via high density EMG, as we normally do. And then that's kind of the initial trick we did to study this. So you have the spike times from the EMG, and you have both systems synchronized. So you can use the spike time from EMG on the ultrasound images. So you can do a spike trigger average, not on the EMG to get action potentials. You can use on the ultrasound, right? You can leverage the fact that EMG works, validate it, to see, okay, if I perfectly knew when in time each spike of this motor unit was, could I still be able to see something in the ultrasound image without even knowing how it should look like or anything at all? We're just kind of leveraging the fact that EMG, we know it works to get this done. So again, an explanation of everyone knows I think this explanation has the motor commands, final port, action potential, your high density array, decompose the units, put the probe again cross-sectionally to the muscle. You should see, as I mentioned before, kind of the bulging of the fibers when they contract, and you hopefully would see some actual movement on your ultrasound images. So that's just a photo of the setup we did to study this. Very classic. So there's two grids here, up and down, the ultrasound probe in the middle. At the time, there was no easy way to put them together. Also not, at the same place. Also for this, there was no need to put them in the same place. And we had someone doing some contractions, right? And I think, again, at this point, it's important to note, because we want to go for something very basic, we decided to go for like a motor unit feedback approach. So you do decomposition, 10% MBC, initialize your separation metrics, check if the decomposition works, and then you ask participants to control individual units, right? So when we did like most participants had between 6 and 8 motor units decompose in the situation. It was very low contraction forces. And we asked participants, so contract one unit, so the first one you recruit, and stay stable with just that unit for 60 seconds. And record the 60 seconds. Now rest. Now let's do 2 units. So record the first one again, but now the second one together. And 2 units again. And then 3, 4, 5, 6, up until they stop, which was normally at 6 or 7. That's when we stopped doing this. The images, as I mentioned, we're looking cross-sectionally. This is the TA, very easy muscle to work with. That's just the other view of the TA. So you go for that. And specifically, right, because in this experiment, we are relying on EMG firings, on EMG decomposed firings, we know that they can only happen at the top portion of the muscle. We know that the EMG will not be able to decompose anything from this. So from this initial study, we just cropped the initial part of the muscle. And I mentioned before, spike trigger average with the EMG. And that's what we see. And you may all be confused. It looks like nothing. There's just nothing here. Like most of the movement you saw was here, which is the bone, which is, I don't know, it shouldn't be moving or you don't want to move it. So at the initial point, it just doesn't seem like it would work. However, when we have more time and more attention, instead of just doing these videos, you can look at the pixels individually because you have a lot of time. So if you look at individual pixels and you get lucky and you find some good pixels, you see something like this, right? So in orange is the movement of the pixel over time, and in the dashed black lines is the decomposed EMG firings. And actually, from this pixel here, it seems that it works, right? You see something like fairly synchronized. And actually, like if you do on this pixel, like on this line only, your spike trigger average, you kind of see nicely, right? You have in black direction potential for the EMG, and then you have in orange kind of the twitch shape from the motor, the mechanical twitch shape. So it seems that the movement is there, but there's a lot of other things, and they don't really allow you to see that nicely. So to kind of solve this, we had to slightly modify the STA approach. So not only we did the STA, like we have your windows of averaging over, but we also got the variance of this. So in essence, we are looking for here for pixels that move a lot, but also that move very synchronously between each spike of your unit, meaning that they move the same way in each of your spikes. We're looking for like high movement, low variance regions, meaning we should get rid of motion that is just extraneous, like the bone moving or your leg shaking or other things. You should focus on like things that synchronize your firings. And this indeed works. So you can do this from with motor units, and now you have these kind of maps that can show you like specific different regions where you have like a lot of this movement. So probably regions that move with the motor unit. And if you were to look at the time component, so instead of just a spatial one, the time component of this, you would see the twitch, right? And that's what we did, right? Remember, if you go to the protocol, we had like 1 unit, 2 units, 3 units, meaning that for a lot of units, we could track them along the different contractions. So you got the unit number 1, the lowest one, the first one you recruit, it show up in all contractions. So that means that we could track how this maps looks over different contractions, just to be sure we are actually finding something, and it was just not craziness or like it was not super variable. But it proved to be reasonably consistent, both in the spatial domain. The regions you would activate between each activation were fairly similar, and same for the time domain consistent. So the twitch shape you would see was also fairly consistent over the different trials of your units. Again, this was very low force levels. Maybe recruiting 6 or 7 motor units was like less than 10%, like close to 10, but less than 10. As a second point of showing the consistency of this, we also show that you can define some, maybe features from these twitch shapes, and you can calculate this. So that's it. And you see some reasonable values for them, comparable. Some of them are hard to compare, to be honest, because there's just nothing similar in the literature. Maybe the most interesting thing you can calculate from this is we call activation delay. I don't know if there's really a name for it, to be honest. It's a shorter version of the neuromechanical delay, right? You normally do neuromechanical delay between your action potential, so here is gray, and the joint force, or the force at the joint. But that requires like the fibers to contract, cause a movement on the muscle, transmit this over the fibers, transmit this over the tendon, and reach the joint to impart force. The activation delay here is a way shorter time frame. It's just between the action potential and the first noticeable booking of the fibers. So it's basically like the shortest time between one and the other. We finished this, and we had some very nice, interesting results, right? We saw that, hey, we can track the twitch profile during this voluntary, and important to note, tetanic contractions. So when you are voluntary contracting, you don't wait, like, the firing doesn't wait for the twitch to stop to have a new one. So firings will just kind of overlap each other, because if you go here again, right? This time support of the twitch, it's way longer than the time support of the action potential. The twitches tend to last up to like 100 milliseconds, depending on how when you measure it, sometimes more like 50. Also, we see that twitches are present above noise level. We can actually see them. They look fine. And you can track motor units spatially along like the region where they belong to. However, there's still a big open question. The twitches are absolutely not simple. They vary a lot between them. The way you record them, they do vary. And there's a lot of overlap between the units. And we don't really know how they interact, which kind of led to the second approach. It was a bit investigating a bit more about this specific questions, right? So we wanted to know, because it's not really, we don't really know at least, if you have 2 units together, for example, how do they interact, right? For the electrical action potentials, like, with the EMG you measure, it's just a linear summation. You have the units, they have electrical potential, they transmit, attenuate over the tissue, and they sum together, and that's what it works. But this is like a mechanical movement, right? And not only that, like, it's a projection, it's a 2D projection of these mechanical movements on your image. So it's definitely not like as simple as that. So we wanted like maybe go specifically into more details and investigate this. And specifically also we are interested about force levels. So how force levels or how different units like appearing at different times would impact the signals you would record. Similar approach, 2 grids in the lab. EMG in the middle. We also did intramuscular EMG in one participant just to also test. But this time we had a wider range of force levels, from very low to like a bit higher force levels. So we could see how this changed in different force levels. What we saw, first, we could still, even between 2 and 20%, we could still see the units in basically the same places over the different contractions, right? So if we track the unit at 2%, 5, 10, 20%, the same one in the case that where they appear all forces, you could see they have a very, very small overlapping region. And just as a matter of safety, to compare these units, we only use the overlap region between them. Because if we use other regions to compare, maybe the results will be a bit skewed. So we only care about the regions where they were all overlapping in all contractions that we include. And that's what we saw, which is strange. So if you look at this here, this is the spike, the twitch average. So average over all firings, same approach, spike trigger averaging over all firings for one motor unit. And in blue, you can see at 5%, and then in red, 10%, and yellow, 20%. And they kind of change shape between forces, which, first of all, you wouldn't expect. You would expect the twitch just map and mostly similarly over all force levels. Like when you increase force, you just have more units or they fire more fast, but the individual ship twitches shouldn't really change, or at least you would not expect them to, not that much. But they do seem to change, which was a bit strange for us. So if you look at them instead of the average, so for the yellow line here, the red line here, the individual ones, this is an average of the individual, all individual twitches over the firings, right? You can see this kind of, the gray ones, they're a bit all around. There's just a lot of stuff happening, which kind of makes your average kind of low, right? The average is now a bunch of variance. And it kind of shows, so this kind of shows the problem here. So if we were to go for all motor units, all twitches, and we were to compare one twitch to the second one, to the third one, to all, and see how correlated they are to each other inside one single motor unit, you will see that at low force levels, the twitches from motor unit 1 were all mostly similar during the 60-second contraction. They all look similar in shape. But as you increase in force, that was not the case. You will have a higher percentage, so like from 60 something to around 50, then more close to 40% of twitches that are similar. And the other 60% would be widely different. And that's kind of what we see here. So if we break up, so that's the same image as before, the average of all twitches. If we break in two groups, the twitches that are correlated to each other and the twitches that are not correlated to each other, then you kind of see clearly. The correlated ones look nice, look fine. They look the same as the 5% force. But then you have a higher number of twitches that just look like noise, that don't really look like anything. So basically what we saw here, if we again do the same plot as before, all velocities, but now only the highly correlated ones together. You see now they look the same as we would expect. And this kind of shows up that, this show up that at high force levels, the twitch shapes don't seem to change, but you start to find more twitches that are completely uncorrelated. They just seem like noise itself. It's still like a reasonably low proportion, but you start to see more of this happening at force levels, which means that the interaction you have at high force levels is not as simple as you would expect. We can also look at motor units that are close to each other. Because ultrasound gives you position, you can see in the image where they are. You can just select two regions that are spatially close and look at them together, right? So this is a very interesting point here. So in the green line, you have it. This is all about motor unit 1. So this one in the bottom, in those cases. The green line is a spike trigger average only in the beginning part, when only motor unit 1 was active. And you can see it's fairly nice, big. And the gray one here is the spike trigger average when both units are active. And you can see, again, there is a huge reduction on it after you include it. That means that when unit 1 is firing by itself, you have a very nice average, the twitches are high. But when you have two units firing close together, then that means that units interact with each other and kind of suppress the movement that one does to the other and the one to the other a bit. So it's not like a summation movement, maybe sometimes the suppression, sometimes no effect. So it's not as simple as you would expect the interaction between the units. And again, it shows a similar way of kind of showing this. You have now motor unit 1 and 2, and here just the same ones but flipped. What happens here is that if you have the spikes for motor unit 1 here, the STA, the spikes that are kind of closely aligned to the spikes from 2, right? So you have all, 200, 500 spikes for both units during this time. and then you only select the spikes where they kind of happen close together, where they're kind of synchronized a bit, and you do the FDA. You see that one of them, it's normal one, but the other one has like a weird shape. So you see that they affect each other in a sense. But if you flip them around, now you do the same thing, but with motor unit 2 in place of 1, 1 in place of 2, then there's no difference. So now this is a kind of a similar example of a case where motor unit 1 affects motor unit 2, but motor unit 2 doesn't affect motor unit 1, which again, even like complicates a bit more the situation in that sense, right? They interact, but they don't necessarily interact the same way, just flipping them together, which makes kind of a big complicated situation. Anyhow, general conclusions of this, switches from spatially closed motor units do affect each other, but the influence is not necessarily symmetrical and may vary depending on recruitment order. It's a bit of an open question, to be honest. Anyhow, that's kind of the conclusion in the sense from this is like the units interact in complicated ways, but mostly for lower up to 20, 30% force we did, most of the spikes, most of the things were still reasonably, but still have a good noise, like a low noise level. You could still see them fairly well, which kind of leads us to, okay, so it seems like even at reasonably forces, we could see the twitches, we could identify a lot of them. How do we do the magic? How could we go from the image to the decomposition steps? Like that's basically the goal here, right? We don't want to rely on EMG because it wouldn't really solve a lot. So given what we know about EMG, we're just like, okay, it's kind of a similar problem. It's not that different. Maybe we could do something similar. And that's basically what we try. So we try a variation of blind source separation, fairly similar to this one on the EMG signal, on the ultrasound signals. I've not go super details over this because I think it'll be too long. But in general, the idea is similar. Your signals here, your channels, instead of EMG channels, are pixels of the image, right? So you have pixel number 1 here in the corner over time. That's channel 1. Pixel number 2, channel 2, 3, 4, 5, 6. Two important points about it. Because the image is big, you have like 200 by 200 pixels, right? That's like thousands of pixels. You would have thousands of channels, which is kind of hard, meaning that it would not really be possible to extend the channels as you do with EMG. Extending a couple thousand channels is infeasible. So the approach used here is a sliding window. So we do a window for 10 by 10 pixels, a small window, 3 millimeters window, and we do the decomposition on the small window. We slide to the side by 5 pixels, so slightly overlapping the windows, and we do this again, and we keep poking over them. So in that situation, you have like 10 by 10, which is 100 channels. You can extend by 10, 1,000 extended channels. It's reasonably to compute. The rest is fairly similar. You extend, you whiten the PCA. In this case, we whiten and we got the first 70% of the components. We got rid of the rest because it's kind of noise. And then we do the point iteration to decompose it. And this was done in the same data set as the first experiment, meaning it's also like a matching. So you have the EMG and the ultrasound together, right? Means we can validate that this works at all by looking at the EMG decomposition results. And it seems to work. You have your EMG spikes in red and the decomposition results from the ultrasound in black, and they seem to match very nicely. And you can do like that again. This is a two-source validation approach, right? You can get the spikes that are in common to EMG and ultrasound, so the ones they agree on. And you can see that they have fairly reasonably coefficient variation, the charge rates, and similar pulse-to-noise radius. Even the other units, the ones only ultrasound found, or only EMG found, they are a bit different, but they kind of go in similar distributions. They are not expected to be the same because they are different units in a sense, right? The ultrasound ones are kind of deeper units or different situations. Similar idea, if you track the rate of agreement and the number of fires from the you identify, you see for most of the units we found, they had a high, more than 90% rate of agreement. And you identify more than 90% of the EMG findings from the ultrasound. And I think that's basically from these 3 slides, that's basically the most interesting and important part to be thinking. Why would you even try this with ultrasound, right? Maybe I glossed over a bit in the beginning, but that's basically, That's basically the region, right? EMG firings, you detect most of them because you know where they are from ultrasound. We can just match them and find the average depth of the units from the ultrasound image, right? And you see that the ones detected for the EMG were very close to the surface, as expected. There were a couple of units that were a bit deep. This could mainly be because ultrasound and EMG were not in the same place, meaning the fibers are a little penetrated in the TA. So it just could be a case that EMG detect a fiber that was surface in this point, but when it reaches the plane of the ultrasound, it was a little deeper. So that just could be the case. But again, you're mostly constrained to superficial ones. However, ultrasound is not. There is no, attenuation doesn't really play much of a factor in ultrasound. I didn't mention this, but when you make ultrasound images, you correct for attenuation. You do something like time gain compensation. You compensate for attenuation because you know the attenuation of sound in tissue. So it doesn't really matter a bit of the depth. You can kind of get a lot of it. And this is actually a very nice, interesting plot, right? So we kind of did the opposite here, right? In the first studies, we're relying on the EMG spikes to STA the ultrasound. Now we used the ultrasound, the composed spikes, to STA the EMG. And as expected, for surface units in blue, you see very nice action potential, looks nice. Go deeper, it starts to get lower. And I'm not fully sure, but I think the 24 and the 31, they were not detected by EMG, right? So they were units that were not in common. EMG did not find them. But if you know precisely the spike in times from the ultrasound and you STA the EMG and you STA them together, you can kind of see a shape that kind of resembles an action potential. So, if you could anyhow know the spikes beforehand, there is still signal in the EMG. There's likely a motor unit there. It's just that because of the attenuation and the noise level, it was just not detected. It was just not, high enough amplitude to just see something from the decomposition. And now we go break. And then we go to the next portion where I will stop talking about long processing pipelines and decomposition and kind of try to answer a bit of the question. If someone came to you and say, hey, you have 3 years to make a system that will control a prosthesis. It has to control in real time. So you're kind of constrained to like something wearable and something that can work in real time. So how would you do this and why would you do this at all? All right, so moving forward, so we can finish and get to lunch. Second part. So as I mentioned, very nice, decompose, pretty cool for like medical studies, physiological things, very nice. But if we're talking more about the translational side of you, can we use, could you use this like prosthesis control? To be honest, could use this to play a video game? You have some constraints. You cannot have a massive system like the Versonics. So the ultrafast is done on this Versonics, a couple of you know it. Massive system, weighs a ton, requires a bunch of power, processing the beamforming. It's not instantaneous. Everything takes time. So it's not really real time. It doesn't take, days, but it's still, it's just not close to real time yet. So if we're talking about portable wearable systems and real-time processing, what can and what could we do, or why would you do this at all? Okay, so translational challenge, moving from laboratory work to real-world control scenarios. And again, as I just mentioned, decomposition, amazing, it's fun, but it could be potentially great, as some of you know, for controlling interfaces, right? It's a way of extracting features that are like invariant over time. You extract a motor unit today, it's the same one it's going to extract tomorrow. It's a pretty nice way of controlling things. But there is a number of practical limitations. The same ones that EMG has basically still apply to ultrasound, apart from the advantages on the separating and depth, like no invasive and depth. You still have limited performance on higher forces are likely. The validation so far, very little. The B-mode probes you need to use are kind of large, bulky, not really made to be wearable. The acquisition system, gigantic, and the processing is pretty slow. It's not really real time. However, go back to the beginning. To be honest, ultrasound, before we even did it, ultrasound, it still can be used to see growth, muscular movement, right? So that's just the perpendicular. You see the fibers. I think people talked about this yesterday. You can see fibers changing around and moving. If you put again in the cross-sectional view, you can see the cross-section of the muscles. Maybe here it's a bit hard to see. This is the muscle. I think I was doing an extension movement of my wrist. And in the video, you could see the muscle was like deforming while I was extending and resting again. So meaning if you can record this, could be able to control something. And yes, people thought about that a while ago, to be honest. So someone thought about that in 2006, and was not the first person to image muscles with ultrasound, but the first one to do this in a kind of a control perspective, right? And it's a very interesting one, right? So it's a very similar setup as the video. You put a B mode clinical system, one you find in the hospital, put on your arm, you put some markers so you can track your extension movement of the wrist, have a few participants move the wrist. And in this case, if you do like maybe the simplest way of tracking things, put 2 blocks on the skin surface, a block from the end, it was the extensor carpi ulnaris. You put the block here, you track the block's movement over time just by correlation. You can kind of see how the muscle boundaries deform in a sense. You have a number kind of showing how much deformation is happening. And if you plot this together, it's together with your motion capture, the angle of the wrist, you can see that the movement is pretty similar. And not only the movement kind of tracks nicely and is similar, I think that's maybe the more interesting thing to would show is that it is fairly linear, meaning that like a linear change in the muscle boundary is a mostly linear change in the angle of your wrist, which makes the problem incredibly simpler than if it was like a complicated thing, right? If the muscle will like deform a bit and then like weirdly change shape for finishing the formation. So the fact that this happens is pretty useful and kind of increases the potential of this actually working. And yeah, people have done it. A number of people, not that many to be honest. That's mostly all the literature on this since then. There's a couple of 2023 that I haven't included, but people have tried different setups, mostly, clinical systems. You can see the clinical ultrasound probes in the arm. And I will talk about this last one because I think that's like a very interesting one, right? It's a more recent one. The first time that someone, it was I don't know how to pronounce it, sorry. It showed 2 years ago, actually controlling a prosthesis with this. It's a very simple setup. You put the ultrasound probe, you have a socket, you have your prosthesis at the end, and you just do different gestures, right? So they're just literally controlling rest, point, and tripod gestures. And you have your image. You can do, I think in this case, they just did some feature extraction and ISVM to kind of gesture classification, and you can control it. And it does work. Well, if the video plays. Okay, so, all right. And you can just see an example. So they show for the first time that, hey, just like you do with BMG, you can kind of more or less control a prosthesis just by the muscle deformation you're doing with your arm. Which is pretty nice, kind of shows really that it actually kind of could work in the real world, right? And there's a very kind of challenging thing because, he's moving around a lot. It's not just my hands on the table, you're moving a lot, you're doing other things, and he still can do that, which is very nice. However, there is a couple issues with doing this. So issue number one, doing this with the imaging, the probe size and weight. Probes are heavy, medical systems are big. So it's still not really wearable, right? You wouldn't, if you were like an amputee participant, a limb loss participant, you wouldn't walk around carrying a system like this just to control your prosthesis. That's definitely not reasonable to do. I want to highlight that there is some very recent solutions to this. So not to discredit the approach, the B-mode approach. There is some solutions. There are some very recent portable systems. That's actually the one we use. And way more recently, literally a couple months ago, there is some people doing very portable systems that can do some images, lower quality, but can still do some images. So just highlight that this is something that is being fixed recently. The field of, maybe it's a secondary point, not related, the field of wearable ultrasound has really kind of taken up a bit last year. There were like 3 major publications on high impact journals about like small probes just touch your skin and you walk around and you jump and you do a bunch of stuff. And it's still really not there yet. Most of them have some major caveats, but it's pretty nice and it's like a very thing that will probably continue very nicely for the next couple of years. However, there's a second problem that is not easily solved. If you have an MRI, my arm here, an MRI of my arm, my muscle is more or less segmented. I'm going to put the ultrasound probe on it, just an example. Put this probe on my arm. You're kind of imaging a very limited view of your arm. You don't really, imaging a couple muscles, which is not the best. Most movements will happen in other muscles, and you are only seeing a couple of them. And also, to be honest, you can put 5 of these probes, but come on, you don't 5 of these, the systems will be 5 times as bigger. The computational will be like insane. Then you have to match the images together, it would be like kind of hard to do. You could technically do it, but it not really solves many problems in a sense. However, someone, again, everyone always thinks of a problem and finds a solution. So someone found a solution also a couple of years ago. So that's the first time someone did A mode ultrasound for control. So if you remember from the beginning, A mode is where you have only a single line, meaning way less processing. It's just a single one, so it's way smaller and it's way more variable, right? And if you have a single line, you can also just put more of them around. And it's kind of easier to handle, right? So this one, they kind of, the methods were like very similar to that first one I showed, where they had someone with one, this is a Waymo sensor here, a small one. They put it here and they had just a different way of measuring the wrist extension. And similarly, that's kind of how you see the A mode. You see some reflections from the fat in the beginning of the skin, and that's kind of the end of the muscle or bone interface. Pretty hard to say in the A mode. You don't really know where the reflections are, but you can kind of see it and you can kind of track this interface, right? So that's a very simple case. They just track the interface with correlation over time and get something pretty similar to that first study, right? They could track the wrist extension angle very nicely with the AMO system. Now they use like a bit more complicated methods to track them, but the approach is similar, right? But this time, very small system, one channel recording is pretty easy. You don't need to record 200 channels and make an image out of it. Which leads us to the application. Okay. Before I go, a small disclaimer. People have done bracelets, A-mode bracelets. I'm talking about the one we did. It has some advantages to other systems in some senses, but it's not the first one. That's our approach, an ultrasound bracelet. So you have your A-mode sensor. So that's another example of the sensors. We can have a lot of them, right? It's single sensors, recording 24 in this case, 32 channels. It's still wearable, right? It's way less than a 256 channels or 126 channels of an imaging probe. So you can do a wearable system, fairly portable one. You put the sensor around the arm. We kind of imitate the design of like the bracelets, the Mayo and the other bracelet. Put all around your arm. You have sensors for all the muscles. Hopefully, with this, you should be able to control something. And that's kind of a new thing we did. Something interesting to highlight. So this animation here, it shows how we normally do A mode, right? A mode normally is one sensor. This is, this system, our system, older systems use more sensors, but you kind of treat systems as individual ones, right? You make a line, you only care about the reflections that come and go to the single transducer. If you do this, you walk around, so 1, 2, 3, first transmission, a line, and then subsequently you have N lines, you have N transducers, right? Okay, you get the data. However, you could kind of borrow an idea from B mode and kind of put it in the system, right? So what if you record from everywhere in all the transmissions, right? As I mentioned in the beginning, while we are mostly interested in the reflections of the thing that go and come back directly, there is still other, sound does more things. They scatter to the sides, they transmit through the arm if they don't hit a bone. So you could still kind of see reflections in the other transducers. You just normally don't record them, right? They are like independent. Normally you have like a multiplexing. So there's just no actual way to record multiple channels. You would need like actual 32 ADCs to do this. So we did it. And now what happens here is that if I transmit with one transmission generates and receiving channels. So we kind of expand a bit how much we can record from a small number of transistors, which would hopefully enhance what you can extract from this and how well we can control this. It will kind of allow a bit more redundancy, right? Kind of even A mode lines, if things move a little bit, it's very sensitive, right? Because it's an image, right? If things move a bit outside of the line, you lose the reflection. But if you have a number of lines, even if things move a bit to the side, you're still going to have the scattering reflections and other reflections. So you can track things a little bit better than with just single lines without using 100 channels. You could use 100 channels, but whatever. So in the end, if you are talking about doing a single frame or a single image with the system, it's something like this. It's not really an image, it's like a kind of 3D. You have channels, you have transmissions here, and you have like your time component or your depth component in this case. And okay, we have a system. Let's put everything together, right? The way everyone does to validate control. I don't know, maybe not many do cloud control, you normally have an offline experiment, right? You put someone in a recording system, maybe you ask them to do gestures. In this case, we wanted to be a bit more complicated, so we went for a motion capture system, put markers on the arm. And because not only we need to show this works, we kind of need to compare it to something that we know it works. We did 2 times, so one high density EMG and 1 time the ultrasound bracelet, right? So different participants either did the same things with the high density or with the ultrasound. And that's basically what they did. They follow a couple of videos for guidance. This one doesn't have the markers, but we track the markers. And from the markers, you can calculate angles. In this case, movements always involve wrist. So flexion, extension, pronation, supination, radial, ulnar deviation, and open closing of all the fingers together, not individual, all fingers together, right? They did a number of 26, 28 movements, I think. Each movement was 5 repetitions of something, same thing. And because it's offline, you have all the data. After you collect it, you can spend all the time in the world, and at the time, a lot of time, to make a pipeline, right? Try different ways to process your raw ultrasound, get things, move everything, window, extract things. And we try a bunch of things based on EMG, based on what people have done on ultrasound before. And in the end, we arrive at this kind of pipeline that, again, quickly go over it, some basic pre-processing. I maybe have glossed over it, but this bracelet here has 2 circles. This case, the circles are fairly bit separated, meaning that the reflection from one circle doesn't really reach the other a lot. You still see a bit, but the signal is pretty low. So we broke this in 2 bracelets. It's like wearing 2 bracelets in slightly different positions. So that's just filtering this to get rid of that. And then we do some noise correction and delay. So as I mentioned before, right, because of this transmission approach we have here, right, when this wave starts walking here from this transducer, it immediately reflects back, right, because it's just in front of the transducer. So immediately from time zero, you start receiving reflections. But because these ones are like spatially distant, it takes some time for any signal to arrive to them because they're far away. So we do here just some correction to get rid of that. At the beginning, it's basically zeros. There's no reason to process zeros, just threshold them out of the data. This is a fairly standard approach for processing a mode. You just move the signals a bit and you envelop them with like a Hilbert transformation. And then very classic EMG processing. In this case, you don't window the channels, you window the lines, and you do a feature out of each line to reduce the dimensionality to something manageable. However, because it's still, 24 by 24 channels, which is hundreds of channels, each channel has like, I don't know, 20 or so windows. It's still like an absurd number of features for a single frame. So because we didn't have infinite data, for sake of dimensionality reduction and actually having meaningful information, we did a PCA and kept the first 100 components or so, actually 100 components here. And they were the ones that kind of really helped. We try with more, doesn't really change anything. And then you can train a machine learning model, this case, simple one, linear regression. It kind of feeds back into the first work that people did, showing that, hey, these movements are fairly linear. So if they are fairly linear, let's go for linear regression, right? There's no reason to get complicated if the simple thing works. And we did it. And here's just an example of one movement. I think this was the flexion extension movement. So you can see here on top, one participant doing. In blue, the prediction from the ultrasound. In orange is the mocap, so the mocap angles. And you can see it follows nicely. EMG1 also follows nicely, but maybe not as closely. And if you do for all movements, for all participants, you can plot a graph and see how well they compare. And so here it is. So you can see both the ultrasound here in blue and the surface EMG. 2 important addendums. This was, we collected with the high density grids, but we did bipolar. So we got channels around the grid and did the bipolar signal for them. It was a bit easier than using the high density. It would be more comparable, right? Because we have 24 ultrasound channels. So we wanted 24 EMG channels. We did with the high density grid. The results are just slightly higher if you have all your, this was 3 grids of 64. So if you have your 186 channels, it's just a bit higher than this, but it was still different enough. Second point, the second point is that this is a case that it's good for ultrasound and not necessarily good for EMG, right? When you do control with EMG, mostly is gestures. EMG is very good at gesture recognition when you have a limited number of classes and you can separate the classes together. EMG does this well. EMG is not as good for tracking position, which kind of makes logical sense in a bit because EMG is more about the force you're protecting, and the force doesn't necessarily translate with the angle of your wrist, or not as easily as ultrasound translates, right? Because ultrasound is morphological. Your wrist, it kind of tracks linearly with your movement. So it's a good case for the ultrasound in this situation. That's why you have like a reasonable difference between. Because also for completeness, we also needed to justify why we have our multiple receiving approach. So the multiple, the single receiving is like a special case of the multiple one. So we can just get rid of a lot of channels and basically fall back to a single receiving approach. We compare both. In some of the cases, it was significantly different. So having the multiple receiving significantly enhanced performance. But because both were fairly high in the situation, it wasn't that hard of a test to follow. Some didn't show a difference properly. It would need to be something harder to kind of for sure prove it. As a second addendum, our system has considerably more channels than past works in this one we did. So we also had to justify if it makes sense to use a lot of channels. Other works kind of stop at 8. So we kind of a bit more. So, and we see that if we just, instead of not using all channels, it's offline, just get rid of a couple of channels randomly, do all possible combinations of 1 channel, 2 channels, 3 channels, get the accuracy that are required for tracking. And you can see that there is a very good increase. And it is still, I think it's still significant up into 14, more than 14 channels, didn't seem to change anymore. It could just be because it doesn't change. It could just be because we kind of got to 1, which is the best that you could do. So it could just be both of them. So it maybe don't need 24, but you definitely need more than 8 or so. Somewhere around 16 sounds like a reasonable number. And okay, so second thing, we did online, we show it, but we did offline and it showed that it kind of works. But offline, kind of easy. It's the same, participant did 5 times the same contraction. It's basically the same. You are training on 4, testing on 1. You can make anything work offline if you try enough. So we wanted to show that this actually works in the real world because that's the point of this, right? To control a procedure, to control again. Offline is just not enough. So we did it. We did, in this case, 3 dots, not 4. So simultaneous 3 dots. Flex, extension, pronation, supination, hand open, close. 8 participants did this one. The other one was 8 for EMG, 8 for ultrasound. This one is 8 different ones, not the same ones. That did this control one. And we did this, it's called target achievement test. The picture here, I don't know if you guys know about it. It's like a standard way of validating control on virtual environment or like in a computer, not actually controlling something. You have like in this case, a 2.5 3D space. You control your dot, so the blue dot. If you flex, the dot moves to the left. If you extend, the dot moves to the right. Up and down is pronation, supination. And the red circle is the is opening and closing, right? Hands open, the circle is big. Hands closed, the circle gets smaller, right? And you are basically controlling like minus 100 to 100% flexion extension, 100 to 100% here. And the open close is 0 to 100. And participants, they did some training. It was like 2 minutes of training, just basically doing the movements. So we put it on, you train the system, just follow the line. First part, you follow the system to provide training data. And then they did the test, hitting 26 targets. They had 30 seconds to read the target. They had to stay there for half a second or so. And the targets were like, if you have a target on this line or on this line, it's like a 1 DOF, right? You only need to flex or maybe only need to extend. If you have a target like a long 2, you have 2 DOFs because you need to both flex and extend together. Again, that's an important point. This is position control. So there's 2 ways to control procedures or something. There's acceleration control, velocity control, and position. Acceleration control is like a joystick, right? Like when you have a joystick, you are aiming at here. You put the joystick to the side, it moves. You let the joystick go, you're still here. You're still in this position. You don't need to do anything, you're still here. If you want to go back, you just move again, and you're here. Position control requires constant control, right? So it's just like you do your hand. If you want to keep your hand extended, you have to keep extending your hand. It's a bit more natural because that's basically how we control things, but it's definitely more challenging. With acceleration control, you can kind of slowly get to where you want. Like you tilt a bit, you move, you tilt, you kind of correct yourself, right? When you're using a mouse, just like on a mouse, you can kind of correct your position slowly. For position control, you have to perfectly match all 2, 3 dots to that position. So we did it, people did it. And sorry, this video won't play here because I think the format's a bit different. It just shows the participant tracking it. I think there's another one showing this later, so we can use that other one. That's just a bit of the results. It's just showing the path participants take. They always start from the middle, right? So the middle, and then they go and when at one of the targets. You can see they kind of track. Sometimes it's a bit hard to kind of reach exactly the position into, but sometimes it was like pretty simple. They oops, jumped the position and got the target nicely. This is the average results, right? So completion rate is how many targets they got, and time to completion is the time it took to get the target. This one was only ultrasound. We didn't do EMG for this one. This is fairly similar to another. I didn't put here another work in the literature that did very similar targets. They kind of got similar targets so I could compare to this to us in similar scenarios with high density on the wrist, on the forearm, and one DOF results fairly similar. EMG could do very nicely. It could control, I think, even 96%, a bit more on one DOF. But the story changes a bit when you're talking about 2 and 3. When you try to combine 2 DOFs together, like flex and pronate, or flex, pronate, and close the hand together, the completion rate for the EMG was drastically reduced. I think for 2 DOFs was 50%, and 3 DOFs, they only reached 30% of the targets. But the ultrasound, again, it kind of aligns with the idea, right? EMG, you're not doing anything, you have no activation. You are activating one DOF, couple channels you activate because the muscle is active, and which is nice. But if you're doing 2 DOFs together, then there's like more channels activating. So there's just a lot of signals overlapping and the crosstalk again. It starts to get complicated to control nicely. Things get jittery, you don't reach the position you want to. But ultrasound is always there, right? You know, EMG, no movement, no signal. Ultrasound, it's an image. There's always an image there. So we're essentially always controlling 3 DOFs. So if you do well on 1 DOF, you're going to do well on 3. If you don't do well 1 DOF, you're not going to do well on any of the DOFs. So it's more like either it works or it doesn't work. And anyhow, all of this still virtual control. And virtual control is a bit easier, right? This case, most cases, you put the hand on the table and you just move around. Like you train in this position, you do your targets here without moving around. It's kind of stable, things don't move a lot. If you want to move for like, in this case, prostheses or other things, the system has to be able to like detect your gesture here, or detect your gesture here, or detect your gesture there. And that's not easy to do. So that was the next step to try to get there. For able bodies, we tried. Now we have videos. This example of someone trying to control 3 DOFs. So the same 3 DOFs, pronation, flexion, extension. It kind of works. Not, you can see sometimes the hand doesn't really do what it wants, but it could reasonably move. It's considerably easier for 2 DOFs. So that's a 2 DOF control, only pronation, supination, and closing. It's very smooth control. It's someone me. No, I did this a lot, so I'm trained, so that's why it's good. But with enough training, yeah, maybe most people could, maybe most able bodies could do that, like very nice, very smooth control. One thing very nice about it is that the pronation supination control. A couple of the papers have showed this. It's really good for ultrasound. It's not good for EMG, but it's really good for ultrasound. In the other case, hand opening and closing, it's a bit more hard to ultrasound, but it's way easier for EMG, right? So it's that kind of the situation that highlights how different the techniques are and how they just, not competing with each other in a sense. They could definitely be used together because it would be better. It's just showing, again, as part of this project, he was supposed to show ultrasound, but they can definitely be combined. It would be pretty nice too. Again, able bodies, we can make it kind of work. We try with limb loss participants, so that's an example. This video, again, sorry, this one I don't think it will play, but you can see this one is similar. The only difference that this one, we made like a virtual environment for the participants, for the amputee participants. They felt that this kind of 2D environment was a bit confusing and a bit hard to grasp. So we just made like a 3D hand, so they could both see the hand and the training was more easy, right? They don't have a reference to what they are actually moving, so it's way harder for them to train properly. And we just kind of playing around a bit when we start trying this and kind of show that it kind of works nicely. However, when we go to this one, Yes. When we try to put this in a socket and have the participant move it around, fast forward a bit, you're gonna see that it wasn't really working super well. He could control it. He could maybe do a couple blocks, but especially the pronation explanation again kind of works nicely. He could control well, but the hand opening closing, which is very necessary for daily tasks, wasn't the best. And it was a number of problems we kind of found that we found with this socket. It was mostly like practical things, right? This socket was just not fitting well. It was leaping around. There was just not enough place for the sensors. We had to put only 12 here, and they were also moving around a bit, just moving around, which is horrible even for EMG. Sensors move, signal is destroyed. You have to train the system again, and also it doesn't really cover the stem. And that's something really, I think that's kind of a bit of what we learned from this is that sometimes you do things in able bodies, and when you try to translate to a specific patient population, think, oh, it's probably similar. It really is not. So for able bodies, doesn't really matter if you put the sensors here, a bit lower, a bit lower, a bit lower. Your muscles kind of go from here to here. It'll be a different signal, but it will be highly correlated. It's still the muscle moving around. That's very much not the same for this type of participants. Because of the different situations they had for the amputation or how they got there, the muscular morphology they have is widely different. I think this is a very interesting case because in this case, the signals we could get, like when he was trying to pronate supinate, it was a lot of change very close to the elbow. But if we asked him to imagine opening and closing of the hand, it was nothing was moving. There was no movement at all. However, if we move the system from the tip close to the elbow to close to the tip of the stump, then it was the opposite. There was no signal for rotation, but it was a lot of signal for the opening and closing, which kind of highlights that it's not as simple as just putting sensors in a single band. You really need to cover a bit more and be a bit smarter about it. So we decided to change a bit the fabrication. Instead of using the kind of the 3D printer in that case socket, we went for the kind of plastic clinic socket, the kind of the thermoplastic socket you cast it, you make the thermoplastic and you cast it the shape. And instead of making a bracelet of sensors, let's just put the sensors all around, right? We have 32 sensors, we can definitely cover everything. And that's what we did, kind of a constellation of sensors. And that way we will hopefully sample everything we need. Maybe a bunch of stuff we don't need, but at least we sample everything we need. And we did it, and we have the full socket here in the view, with the chemical engine to control it. And we had the participant move. That's just the general results. We were able to get reasonably offline performance. We trained and test the system offline. It was a good performance. He did the tech test again. In this case, only 2 DOFs. We didn't get to 3 DOFs with him. So it was only pronation and open and closed. And he did the tech test. Good number of targets, less than able bodies for sure, but it's still reasonable. And he was able to complete both the box and blocks and the closed pin relocation, which is the first one you saw me doing the relocation, which is a test that pronation supination really, really needs to get the closed pin from here to here. You really need to rotate your hand unless you want to like rotate your whole body, which is really bad. And that's a video of him doing it. And you can see it a bit better, the rotation, the beginning, ready to do. And then we'll grab it. And it's still not perfect. I think he will drop the second block, but now he can reasonably control them. I forgot to bring the video for the closed pin relocation, but similar thing, he was able to get it. I think he dropped one of the closed pins. He did 3 times. I think one time he dropped one of them, but he got all of them kind of reasonably nice. And that's kind of basically the stage we reached. We did this again, 1 participant only, but we kind of were able to maybe show in the case of A mode for the first time, someone controlling proceeds. It's pretty cool. And there's some other advancements to do this, right? This system is still a bit like a prototype state. We have something I didn't put it here. We did some experiments with able bodies using splint controlling, and also another amputee participant controlling a splint. It also involves some other low-level control stuff. And there's some other human machine interfacing able body controls on the works. And before questions and answers, I just want to acknowledge basically most of the research, everything was made under the like a Horizon project. SOMA involves all these universities, each one doing different things. So acknowledging them, that's the financing, that's the team that work on this. And also acknowledging everyone. This is not an individual effort, it's a very, 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 very group effort. Acknowledging everyone that help in different steps, from transducers, electronics, control, methods, everything. So everyone here and many others that I may have forgot. But thank you so much.